Hi everyone, my name is Ricky, and this is a Neural Magic tutorial on sparse transfer learning. Today I'll be taking you step by step through a Colab notebook on how you can take a dense model and converting it into a sparse and very light variant. More specifically, sparse transfer learning is an optimization method that is not all that different from traditional fine-tuning. In traditional fine-tuning, you have a dense pre-trained model and you adjust its weights onto a new task. With sparse transfer learning, you have this model that has already been fine-tuned on a task, and then you transfer its knowledge onto a pre-trained sparse model. That is sparse transfer learning in a nutshell. And in today's tutorial, we're going to be doing a few things. The first thing is we'll be sparse transferring a dense BERT model that has already been previously fine-tuned on the emotion dataset, which is a multi-class classification dataset. And we'll be converting this model into a pruned-quantized oBERT model from the Neural Magic SparseZoo. We'll also highlight all the important points in training, including hyperparameter optimization and recipes. Finally, we'll benchmark the sparse versus the dense model to see how fast this sparse model really is. The coolest part about all of this is that we'll be using a very simple Colab notebook that anyone can use to perform sparsity on your own custom models. So don't forget to give this channel a follow and smash that like button, and we'll start right now. Okay, so let's get started. First command is to find out what kind of GPU we're working with. In this case, we run the NVIDIA SMI command to find out we are lucky enough to get a T4. The second step is to get us ready for training. So we are going to install the SparseML library with the torch dependency because we will be working with transformers in this notebook. The next section of the notebook briefly goes over recipes and what they are. Recipes are YAML files that have already been constructed by our engineers and are found in the SparseZoo. These recipes contain arguments and modifiers to alter pruning, quantization, distillation during training, as well as general parameters for your training job. And as you can see here, two important general parameters that I'm going to briefly discuss in the next section are the number of epochs and the initial learning rate, because they can be very sensitive to training. But if you want to get more recipes for your own custom model or your own custom data sets, you go onto the SparseZoo and you choose an upstream model that you want to work with. And inside these upstream models, you will find recipes for different tasks. So you have a recipe for that test classification, you have a recipe for question and answering, etc. So this specific recipe that I've pasted here is the recipe for test classification because that's what the emotion data set works with. And these are the default values. Now, in the next section, I'm going to show you the actual CLI command that commences training. And the first thing I want to discuss regarding the recipe is that in this recipes args argument, I have overridden the default values that we just saw above for the general parameters of number of epochs and the initial learning rates. Now, I've already tweaked with this training run ahead of time, and I know that the default values weren't the best optimal values to get the most out of sparsity and performance. And I want to discuss that these two parameters will be the most sensitive as you use your own custom models, your own custom data sets, that you'll have to tweak these two in order to get the best performance out of sparsity. A couple of other arguments that I want to discuss in the CLI command is the distill teacher argument, which will contain the original dense model that we're working with. And then we'll also use the model name or path argument, which will contain the upstream oBERT model that is already sparsified, and this will be the student model. The next argument will be the dataset name, which should be very familiar with you if you've used CLI and transformers, and we'll be passing the name of the dataset called emotion into this command, which automatically triggers the download of this dataset because this is connected to the datasets hub. Other commands that you can find on this CLI commands are the normal commands that you've seen in traditional fine-tuning. I'll leave these default values for now, and we will run this command And it will take training about 55 minutes on a T4 to complete. The accuracy on the validation data set after training will give us an accuracy of about 92.5, which is pretty impressive, given that we were less than a percentage point from the original accuracy of the validation data set, which is around 93% and change. However, we have now a sparse model to work with. How fast? That will be the next section that I'm going to show. So in the next section, after training, is now we want to convert our sparse model into ONNX format, so then we can benchmark its performance against the original dense model. So we have a one-liner from the SparseML library, and we pass in the directory of where the sparse model was saved after training, and we add the task and the sequence length. The next step is to do the exact same thing for the dense model. The first step is to download the dense model from the Models Hub, and we're going to save it here to the dense model directory. After it's saved, we're going to rerun the export ONNX command, and this time we'll have a dense model directory passed in. After running these two commands for the sparse dense model, we'll have the model.onnx file saved in a directory, and now we're ready to benchmark. So the first step is to install DeepSparse, and then we're going to run another one-liner. We're going to run the benchmark command for the dense model, and we're going to run the benchmark command for the sparse model. And after we run benchmarking, we're going to get the output in throughput, latency, and the number of iterations alongside inference scenario and batch size. And it's pretty incredible that after we have our sparse model, we have improved latency of 8x over the dense model. So now we have a latency of 54 milliseconds, where originally in the dense model, we had a latency of 410 milliseconds. So it's a dramatic improvement of the latency. And these types of improvements are very important for our users who want to take models into production, because in production, we all want several things. So we want our models to be light, we want our models to be fast, and most importantly, our models to be accurate. And as you can see, within 1 percentage point of accuracy of the original data set, we're doing really, really well with this collab notebook to conduct sparse transfer learning. So here we are. We just finished our notebook. It was very simple. We have the last section here is just to give our repos a look. Go check out SparseML. Go check out DeepSparse. Give it a star and let us know what you think on our community Slack. I want to thank you again for joining me on this training run to perform sparse transfer learning, and I'll check you out next time. Take care.